Hello. Our lecture today will cover the material in Lecture 16, continuing on with the use of public key cryptography. I do want to wrap up a few loose ends regarding the Chinese remainder theorem from yesterday, and I'll be going through another example with system of congruences with three different moduli, and then move into some of the applications of RSA. So the full version of the Chinese remainder theorem can work for any number of moduli. Here, n1, n2, n3, up to nk will be integers, and I need each of these integers to be relatively prime to each of the others. So if I have an ni and an nj that are different from each other, their GCD should be equal to 1. You could also say that if I have k many integers, I want them all to be pairwise relatively prime. Any two of them cannot share a prime factor. In this situation, a system of k different congruences, the first modulo n1, the second modulo n2, and so on, this system will always have a unique solution x, and the solution will be in the integers modulo the product of all of these moduli. So the solution will come mod n1 times n2 times n3 and so on. To see this in action, let's take an example where I want to find an integer who has residue 1 modulo 9 and residue 5 modulo 10 and residue 1 modulo 11. Any two of these numbers are going to be relatively prime. 9 and 10 are relatively prime. 11 is itself a prime number, so I know that 9 and 11 are relatively prime. 10 and 11 are relatively prime. And the solution that I'm going to find will be some residue or some remainder modulo the product of all three of these numbers. So the solution will be defined up to integers modulo 990. The method that I use is still the same method that I used on yesterday's lecture. It comes in 3 steps. For the first step, I want to find the product of these moduli, excluding one of them at a time. So I know that all three together make 990. When I'm looking mod 9, I want to find the residue of 110. I picked this to be 10 times 11. When I'm looking modulo 10, I want to find the residue of 99. I just picked to be 9 times 11. And when I'm working mod 11, I want to find the residue of 90, which is 9 times 10. And that's just the product of all of these moduli, excluding the one that we're working in. So I take my 990, divide out that 10, I want to find the residue of this number, mod 10, and so on. And those residues are respectively 2, 9, and 2. For step 2, I want to find inverses of each of these residues modulo the corresponding number. So the inverse of 110 modulo 9 I claim is 5. That's because this residue is 2 mod 9. 2 times 5 is 10. 10 is 1 modulo 9, so this is the inverse of 110. It's just 5. Likewise, the residue of 99 is 10 modulo 9. 9 modulo 9. 9 itself is the same as negative 1. I know that negative 1 is always its own inverse. So I'm going to record the inverse of 99 here as minus 1. I'm allowed to use negative numbers, and this will make the formula on my next slide a little bit easier to work with. Then finally, I take my 90. 90 reduces to 2 modulo 11, and I can check that 2 times 6 gives me 12, which is 1 mod 11. So my inverses are now 5, minus 1, and 6. In my step 3, I'm going to multiply each of these numbers from step 1 times their inverse in step 2, just as ordinary integers. So I have my 110 times the inverse of 110, which I wrote down to be 5. And this is multiplied by 1 because I want this number to have residue 1 modulo 9. Then I take my 99. The inverse of 99 modulo 10 was negative 1. And I multiply by 5 because this number is supposed to have residue 5 modulo 10. And finally, I take my 90. I multiply by 6, which is the inverse of 90 modulo 11. And I multiply by 1 because I want residue 1 modulo 11. Put that all together and I get 595 as a solution. So this will be my unique solution modulo 990. This is the only residue in the integers modulo 990 that satisfies all 3 of those congruences. But as long as I have any n which is congruent to 595, that integer would work as well. So if I want all possible n, they'll be the integers of the form 595 plus some multiple of 990. All of the n, according to this formula, will reduce to 595 mod 990. It's easy to see that this has residue 5 modulo 10. I can just take the last digit. If I want to check that it has residue 1 modulo 5, I can just add all of the digits. 5 plus 9 plus 5 gets me 19. 1 plus 9 gets me 10. 1 plus 0 gets me 1. I'm just doing the same reduction technique modulo 9 that I talked about previously. So I get residue 1 modulo 9. And for 11, it's a little bit trickier, but we will also get residue 1 modulo 11. So I can say that 595 divided by 11 is 54 and change. How much is 54 times 11? I get 594. So it must be that 595 has residue 1 mod 11. Let's talk some more about RSA and public key cryptography. Yesterday I went through the setup for RSA just in terms of a generic crypto system. But it turns out that RSA will actually work as our first example of a public key cryptography system. So the setup is I've picked some very large integer, capital N, with the particular factorization n is p times q, and p and q are different prime numbers. The set of all plain text messages I'm going to work with is the same as the set of all ciphertext messages. These are just going to be residues modulo n, or you can write it as residues modulo p times q if you prefer. And as I talked about last time, the key space, the set of all possible keys, are the units modulo phi of n, or phi of p times q. And just as a reminder, these are all of the residues A, which have greatest common divisor of A and phi of n equal to 1. So anything that is relatively prime to phi of n. My encryption function says take one of these exponents, e, raise your plain text message to the power e, and that produces a ciphertext. So here I'm using the letter E for encryption. To decrypt, I need the multiplicative inverse of E modulo phi of n, or modulo phi of p times q. And I can decrypt if I have some ciphertext. I just raise that number to the power d and mod out by p times q. That will give me the original plain text message. Now, the whole point of public key cryptography is that we want to be able to tell other people our encryption key without giving away the decryption key. So this is not something that would have worked when we were talking about affine shifts, because if you know how to shift to scramble the message, you just do that backwards and you have unscrambled the message. It also would not have worked with our one-time pad or the bitstream cipher. The key to the bitstream cipher is the randomness, the random sequence of bits, or the random number generator that you've agreed on. And anyone who knows how to encrypt using that random sequence of ones and zeros also knows how to decrypt. Now, this seems like a strange idea that we would be telling other people how to encrypt in our crypto system. And I want to explain why that's something that we can take advantage of, why that's a good idea. But why would this even work? How is it that I can tell somebody my exponent E without giving away the decryption exponent? How can I not give away D? Because isn't it the case that my decryption key has to be the inverse of E mod phi of n? Certainly if you have this number, you can just calculate this number using modulo arithmetic. The thing to bear in mind, though, is that because we set up the crypto system, we know phi of n. We know the factorization of n. N is p times q. And since both of those are prime numbers, then phi of n must be p take 1 times q take 1. But to a person on the outside who does not know the factorization of n, they cannot use the formula to calculate the Euler phi function. All they know is that n is some very large number. In working practice, you might see, n is some number with thousands of digits, maybe millions of digits, depending on what your use case is. Without knowing the factorization of n, they would have to list out all of the residues mod n and one by one work out which ones have inverses. That's what phi of n counts. We'll talk a little bit about this on Monday, but the short of it for now is that factorization is very hard, and even though there are algorithms that will eventually be able to factor any number, the key word is eventually. We're talking millions of years to factor such a number. So we will be long dead before an attacker can break our secrets, and we don't care as much about people breaking our secrets millions of years in the future. It's just not practical. So an important part of this system is that we do keep the factorization secret, and we do keep the fee of n secret, so that people we don't want to read our messages cannot calculate the decryption key, even if they know how to encrypt for our system. This also tells me that I can't take prime numbers as my capital N. If it was the fact that my capital N is prime, then n take 1 is automatically phi of n. The formula is super simple there. So this is another reason why we use a composite integer n to help obscure the phi of n function. So for right now, let's just say that this is something that can work. We can try to stack the deck so that attackers will have to take millions of years of computation to break our secrets, and then they'll just give up because that's way too long to be practicable, and they'll find some other target or perhaps find a different way to try to compromise us. Why is this a good idea to have a public key crypto system? So this is a table I've taken directly from the notes in lecture 16. If you have a whole bunch of people who want to send messages to each other, but to keep their messages hidden from anyone except the person they want to talk to, we can build up a database of these public key systems. So this is exactly the kinds of stuff that goes on behind the scenes on any number of, modern, popular, end-to-end encrypted chat programs. The computer program will make a database of who all of the users are, and each user will get assigned their own public key system. So person 1 will have the primes P1 and Q1. And once you pick those prime numbers, it's very simple to compute. N1 is just the product of the two primes. Phi of N1 is just the product of P take 1 times Q take 1. Pick some encryption key, just some residue modulo phi of n. And then since we do know this phi of n, we can calculate the decryption key. Now, person 1 has to keep this information private. They cannot tell anyone what their prime numbers are, because that would give away the secret to their decryption key. Similarly, they can't tell anyone their phi of n, because that would also give away the ability to compute the decryption key. And of course, they can't give away the decryption key. The exponent d has to be kept secret. But person 1 will make the following two numbers public. So they need to disclose the modulus n that makes the RSA system work, and they need to also disclose the exponent e. So with these two numbers, any person in the world can encrypt a message, and only person number 1 can decrypt it, because in theory, only person number 1 knows the exponent d1. So this is the reason why companies cannot decrypt your chats on your behalf. They do not have your private key. They only have your public key that your phone or your laptop came up with. It's a bit of a simplification, but for right now we're just working in a theoretical environment. So that's everything that the first user of this system is going to do. The second user does pretty much the same business, but with their own numbers. Person number 2 will have a different pair of prime numbers, P2 and Q2. Person number 2 will have their own n, and their own phi of n, and their own exponent e for encryption, and their own exponent d for decryption. Most of those numbers they're going to keep secret, but they will publish the modulus for the RSA crypto system and the exponent for encrypting messages. So this is the information to send a message to person 2. Person 3 will have their own primes and their own integers and their own secrets and their own published public key. And this will be true for every single person in the database or every single user of the computer program. The benefit of this is that if you want to talk to somebody securely, you don't need to meet beforehand. You don't need to establish a shared crypto system that only you and them know. All you have to do is look up their details in the database. So let's say person 2 has some message they want to send to person 5. 2 will go to the directory of all the public keys, or more realistically, their phone will look it up for them, and get the numbers N5 and E5. These are exactly the numbers that are required to encrypt a message in person number 5's public key crypto system. So since 2 has that information, they can encrypt their message with 5's public key. They get some ciphertext that is complete nonsense to a random person. And since person number 5 has the decryption key, D5, person number 5 can then decrypt the message and get the original plain text that person number 2 wanted to send. Nobody else in this system can decrypt the message unless they have D5, and as long as person number 5 has been practicing good security and kept D5 a good secret and kept particularly their primes P5 and Q5 a secret, someone could leave a computer running to solve for D5 and to crack this system and be able to decrypt every message that person number 5 has ever received. But that would take millions of years, and the attacker would be long gone before they get any useful information out of that. Again, there are some more practical kinds of attacks that I'll be talking about next week. So this is an improvement upon ordinary crypto systems where you need to share your key with all of the people that you want to talk to. That means that you need to find a secure way to send keys to each other, or you'll need to meet in person before you talk. Here, we can just leave a database and any single person in the world can encrypt a message, but only the correct person can decrypt it. Now, that's not the only use of the RSA system or any public key encryption. Could we instead use it a different way? Now, the whole business says we need to calculate some capital N and keep its factorization a secret so that we can play these games with the exponents. What happens if we publish the decryption key instead? And sure, you can say, well, E and D are both integers. They're supposed to be inverses mod phi of n. Does it really matter which one is which? I'm going to keep using the letter D here for decryption. What this looks like is I can put a statement up on my website, and I say exactly what my public information is. I say, this is my modulus n, this is my decryption key, D, and I'm keeping the encryption key, E, a secret. So this is reversed of the way that reversed of the system we were just looking at. So what this means is now every person who reads my website has my decryption key. Any person in the world can decrypt messages in this RSA system. But who would be sending such a message? Who is able to encrypt messages using the encryption key E? Well, I'm the only person that has the encryption key E. So anyone in the world can decrypt these messages, but I'm the only person who could have encrypted them in the first place. Now, what that means is my messages won't be secret if every single person in the world can decrypt them. But what it does mean is that I can verify that I am the only person who could have written a message. So if I want to sign a digital document, it would be foolish to scan a picture of my own handwriting. Even if my handwriting were legible, it would be foolish, because you could just take a picture of that signature and copy it and paste it onto any number of documents. So instead, if I want to make a statement that I agree to this contract, or I authorize this purchase, or I am sending $300 from one bank account to another, I'll write that message out. I'll make sure to put the date on it as well, and I'll encrypt it using my secret encryption key, E. Then I can send that statement to my bank, or I can send it to a store, and they can decrypt it because they have my decryption key. They decrypt it, and it says Thomas Morrill authorizes such and such. I don't even need to hold on to my phi of n after I set up my crypto system for this. All I need to retain is my secret encryption key E. My primes P and Q I can just toss away, make sure I shred them so other people can't find them and use them against me. But by doing the public key cryptography in reverse, I make a system that guarantees authorship. This is a mathematical argument as to why I am the only person that could have sent such and such message. Systems like this, where we can send a message to a single party and guarantee that they are the only person who reads it, or where we can sign a statement and guarantee that we are the only person who could have sent that message to begin with, these get used pretty much everywhere in modern life. You wouldn't be able to run the internet as it exists without these things. You could even combine them. You could have one system for signing messages, and then take that signed message and encrypt it using someone else's public key, so then they would be the only person who can read the message, and once they have it, they could verify that you are the person who sent it. Now, this is not a class on how the internet is built. That would be well over a year's worth of material. But there's an entire industry of these kinds of databases. We use them to make sure that we're talking to the people that we think we're talking to anytime we do stuff over the internet. So any personal, private stuff that you do, shopping online or logging into Facebook, checking your bank account, looking up your insurance records, or scheduling an appointment with your GP. All of that is stuff that really should only be going to one other person, and we use encryption to make sure that we can trust that system. Now, most of that calculation is happening in the background. These days, our computers, our phones, our internet browsers will make these calculations for us and report back that, yep, we did the encryption, checks out, go ahead and buy whatever that thing is. Go ahead and authorize a bank transaction. But the reason that we're able to leave these tasks to computers is because of the cryptography. All right, this lecture is a little bit shorter than yesterday as I'm still getting used to the format. I'm going to post this to Moodle along with the slides from today. You can also expect to see practice questions for next week's quiz. The quiz will be the same format as our last quizzes, so still 2 or 3 questions, still 15 minutes long, but this quiz will now be administered on Moodle, so there's an option there I can have it time you. You're still welcome to use calculators, but it is a closed book exam, closed notes. So please take that quiz using just the things that you have committed to your active skill sets. I'll also be posting some sample questions for our midterm. Presently, our midterm is scheduled for Friday, 3 April. It's not, The school is presently working on ways to administer tests without meeting in person. So presently, I am planning to hold that test on the 3rd of April, and I will let you know if that needs to be postponed for whatever reason. Thank you very much for sticking with me through this. I know it's a difficult time. If you've been having any issues accessing materials online or have any suggestions for improving these lectures, please let me know, and I will try to incorporate those suggestions as soon as possible. Bye.